You're building. One last block right here to finish the wall. Your hand moves, you click, and who really places that block? Let's find out. That block isn't real. Not yet. Your screen drew it before the server agreed. You didn't place it, you requested it. It feels like one simple action. Click, block, done. Your friend sees it, you keep building, and nothing about it feels unusual. But for a fraction of a second, two versions exist. There's the block your computer shows you, and the block the shared world has actually accepted. They usually match. Usually. The moment you click, your computer doesn't wait for permission. It draws the block immediately. That instant block is a prediction, a confident guess about what the server will say. It's like raising your hand to wave before you know whether the other person will wave back. Most of the time, the answer is exactly what you expected, so the guess feels like the truth. And when the answer is no, you've felt this. The block that won't place. The step you take, then get yanked back from. That rubber band tug. That's what happens when the server corrects your guess, and lag can make the correction impossible to miss. The block appears, flickers, and disappears. When a false local block remains visible or suddenly vanishes, players call it a ghost block. So who decides whether the prediction becomes real? Not your screen, not your friends. In normal multiplayer, the shared world lives on a server, a machine in the middle. Think of it as the referee. You and your friend don't send blocks directly to each other. You both talk to the referee. Every accepted change comes back out from the middle. And whatever the referee decides is the truth, even when your screen disagrees. Your computer can claim anything: that you placed a block, that your pockets are full of diamonds, that you walked straight through a wall. But the referee holds the only real world and quietly ignores whatever breaks the rules. That ghost block from a second ago? That's the same no, just in its most harmless form. The friendly little cousin of the same principle that rejects impossible actions and makes cheating harder. And that middle may be far away, through cables, cities, maybe an ocean. Your request is the shout. The answer coming back is the echo. The round-trip time is your ping. If that route feels familiar, it should. It's the same journey a click took in our very first episode. Same cables, same ocean. Only this time, we're chasing one block. Now let's slow that tiny moment down and follow one block from your mouse to the server, and then to your friend. Millisecond 0. You click. Your computer does two things at once. On your screen, it draws the predicted block. Into the network, it sends a placement request, the position, the action, and an order number that helps match the answer to the request. The package leaves. In our example, it spends 30 milliseconds crossing the network. Meanwhile, the block on your screen already looks finished. Your computer is lying to you. Politely. At 30 milliseconds, the request reaches the referee, but the server doesn't advance its world continuously. Under normal conditions, it moves the simulation forward in steps, 20 steps every second. A request can arrive just before one of those steps, or just after it. So the extra wait can be almost nothing, or nearly 50 milliseconds. Ours arrived at 30. The next step is at 50. It waits 20 milliseconds. Then the step begins. The server checks whether the placement is valid. Does the request make sense, and may the world accept it? In this version, yes. Stamp. At 50 milliseconds, the block becomes part of the official world. But rewind the same moment and change one thing. The placement is rejected. Now your prediction has no matching block in the server's world. The referee whistles it back, and the ghost block vanishes. Back on the successful path, the referee now sends the accepted result outward during the same server update. One message back toward you, another toward your friend. At around 80 milliseconds, the confirmation reaches you. If the prediction was right, the official block replaces it so neatly that you notice nothing. No jump, no pause. Just a guess turning into truth. Your friend may be on a different route with a different delay. In our example, the update reaches them at about 110 milliseconds. For you, the block has been visible since the click. For them, it appears for the first time now. Click, prediction, request, network, wait. Server step, check. Confirmation, broadcast. And your friend sees the result. Start to finish, roughly 1/10 of a second. You felt one click. The system performed an entire conversation. And here's the quiet wonder in all of this. You and your friend never actually see the same screen. Each of you holds your own copy of the world, updated at slightly different moments. What you share isn't the picture. It's the referee's yes. Two separate copies, one source of truth, and out of that, the feeling of standing in the same room. That server step changes how the whole game works. Your screen can draw smooth motion whenever it wants. But the official world is advanced in discrete steps. 20 of them every second when the server is keeping up. But why steps at all? Why not just let the world flow? Because a shared world needs one place to decide what happens next, and in which order. Without that shared rhythm, different computers could disagree about who swung first, whose block landed, or which version is right. The heartbeat gives the server a steady drumbeat for moving the shared world forward. It's the thing that turns separate computers into one world. Every 50 milliseconds, another step begins, and the shared world moves forward again. Not one giant freeze, but a rhythm. 20 tiny frame zeros a second, marking the server's idea of time. Every official block, step, and hit becomes part of the shared world on that rhythm. Your screen shows you smooth motion. The server sees steps. One more time at real speed. Watch. Click. Done. Now stretch out that same moment. Your screen draws the prediction. The request leaves. 30 milliseconds to the server. 20 milliseconds waiting in our example. The heartbeat lands. The referee checks and accepts it. The result travels back. Your guess becomes official. And farther away, your friend sees the block for the first time. All of that hidden inside one ordinary click. Remember the block we froze at the beginning? The server has answered. The prediction was right. Let's let it finish. 2 players, 1 referee, 1 block. Simple enough. But what happens when a million people ask for the same thing at the same time? The same video, the same file, the same update. One machine in the middle is no longer enough. So who hands it to everyone? Not one machine, many. Each keeping a copy close to you. So what really happens when you press play? Next time on Frame Zero. Every story starts at frame 0. Subscribe! You know where the button is.